we are, get this out of the way. There we go. Ready to start a new week? Moving along. Let's take a look of where we're at, where we're going. I think we get into a new chapter. So this is our week over here. We're going to get into complex numbers and quadratic functions today. Going to do the heavier part. Then on Thursday, we'll just look at polynomial functions in the graph. So we'll only have one section, which will give us some time to take a look at homework and such. So we should be through 1.2 to 1.8. Is Canvas updating homework scores? Okay. I can't. Some of them I have them, they'll sync. One of my classes it doesn't, so I have to manually do it. So those are getting updated. What do we have a due date coming up? Okay. What I will typically do is I sort of put these due dates on there to encourage you to get done by that date, and it's of course good to do that because it's not a good idea to spend the weekend before the test doing all the homework as well as studying. But what I do is I will move it so that if you still have something you're struggling with or something, so don't worry too much about due dates. Those will get moved another week if you need them. If you don't, that's great. You can always go back and review them, but it gives you, when things happen and you get a little bit behind on something, you'll still be able to work and study. And sometimes it's just one concept isn't making sense, so you keep moving forward. And sometimes that's a great strategy because you get it forward and then now it all of a sudden makes sense. And then now you could go back and do it, but if the due dates are gone, then you can't do it. But I'll keep moving them, so you'll see that happen throughout the semester. And if I'm a little bit slow and a due date passes and you haven't finished something, just send me an email and it'll remind me to, okay, I need to move those till, and I do it up till the time when we have the exam. So we'll have our exam, let's see, we're going to review on a Tuesday and then we take the exam on Thursday, September 14th. So that's kind of the key part we're looking for. Keep learning, keep exploring. It's okay to make mistakes, but let's recover. And again, the idea is that eventually most of it will make sense, hopefully all of it, but that's not always the case. Even after teaching all these years, I still learn. So we've gone through 1.8, which is inverse functions. And again, those there's some prior recordings for most of those. There's the class recording there. There's these additional notes that come from the coordinator that I'm incorporating as we go. And so we're now into Module 2. We're going to deal with, take a look at polynomials and rational functions. Complex numbers, and again, there's some additional resources here that you can take a look at that might help. The review? It might be, yeah, it's kind of light on questions. So it's not, and I'll take a look at that. I'll ask for what the exams are going to look like. So I'll start looking at what's the best way to prepare for the exams and what are the best resources. And sometimes the 20, it helps you know whether you're ready or not, but sometimes you want extra questions. So we'll see what all is available for us, and I'll start beefing that up this week so then we still have a couple weeks to get all that done. And as you saw, there's a few things as I'm going through, like actually this unit we're going to do today, I had to, we do a little bit more, we do more technical stuff here, so I had to update. Yes, sir.
There was a problem at the end of 1.8 that you said you were going to go over.
Oh, thank you. I knew there was something in one of my classes I couldn't remember because there was one I hadn't finished up. So we'll take a look at that. Thanks for the reminder. And then we'll get into complex numbers, and it ties very easily in with the quadratic. So again, we've got 2 days to cover all three, so we're not in any big hurry. So 1.8, we are going to look at the slide deck. And actually, I'm recording this whole, so I'll probably put a note that if you want to see this last part, which is this one, wait, wasn't this one? Okay, gotcha. Now it's coming back. Okay, so this one, finding an inverse of a function, right? First thing we do, rewrite it. I need these, need my writing tools. Come back here. So we rewrite it as y equals 2x over 5x minus 4. And then this is the step that actually makes it the inverse. We just switch the x and the y, and we have the inverse, but not in the pretty form we want it in. So we just change the y to an x, change the x's to y's, and again, that is the inverse. If we had graphing calculators that could deal with this, which actually Desmos can, I believe, and there's some newer ones, so we could, in the future, students will probably be done with the problem at this stage, but for us, we want to get it so we can actually list it as an inverse function, and so what we end up doing is we solve for y. Okay, so when we go to solve for y, you could sort of either cross multiply. What I'll do is I'll multiply both sides by the denominator, 5y minus 4. So this will cancel with this. And I'm going to, on this side, I'm going to distribute the x to both of the terms. So we end up with 5xy minus 4x equals 2y. And again, what's our goal here? We're solving for y. Currently there's two y's, which kind of, now we're freaking out. What do I do? Well, we're going to get it to be one y. What we need to do is get everything with a y to one side. My suggestion is, instead of moving two things, let's just move this 5xy over here. So we'll subtract 5xy from both sides. And we end up with negative 4x. This side that cancels. Then we get 2y minus 5xy. So far now we got the y's on the same side. And this is the key part, which seems, this is the hardest part of it. It's where I got stuck for a long time. But when I saw it, it's just like, wow, you just do it this each time. What we're going to do is we're going to factor out a y from both of these terms. So we're going to factor out the y here and here. So this simply becomes minus 4x, simply, right? We'll factor the y out. You could put it in the front or the back. I'll just put it up here. So now that the y is factored out, I took this y out. So there's a 2 minus 5x. And that's usually the step that's the most difficult, or it's not intuitive, because it's really a backward step. Usually we're distributing. Distributing's not a problem. I just multiply everything through. Factoring's a little harder because we're undistributing, and once you start to see those, a lot of different techniques will be much easier for you. But this is typically what will be the difficult part. We're not quite done yet, but we're almost there. What would we do as our last step to get the y by itself? We divide by this whole thing here. And these cancel, right? So now we've left with y equals that. That's our inverse function. So we could rewrite this as g inverse of x equals negative 4x divided by 2 minus 5x. Okay, so that's the inverse function. Now, the thing is you don't really see, when you look at the two, it might not look like they're really inverse, like when we do a linear equation, multiplication becomes division, subtraction becomes addition. So you can see the opposite, but this one it's kind of harder to see because of all the stuff that went in between. But I just wanted, that's why we could have rushed through it, but I didn't want to, because this part here is really important, because it not only helps with these particular problems, but that's a thing we will see throughout our work, and you'll see it in calculus. It's an important thing, and once you start to see it, it's almost like, how did I not see this before? But until you see it, it's like it's this block that keeps holding you back. At least it held me back for a while. So how's that? Does that make sense? Any questions? Okay, so that should help finalize any of those with rational functions. But it's just, we had two y's, we want to solve for y, so we're going to have to factor, and that happens quite a few in a few different instances, and we go from there. Okay, so that was 1.8. We'll discard. And now we want to go into 2.1, complex numbers, which is more of a review. But as we review, it's also going to set us up for the quadratics, because that's why we use complex numbers. Is we well, let me just get into this. So we're still recording. That's okay. We'll put it all with here. Complex numbers. Complex numbers are made up of two parts. There is a real part, and those are real numbers, are what we're used to, 2, 3, 2.6, all those kind of things. And then there's an imaginary part. And with that, we're going to, the I from imaginary, you'll see that in there. And we're going to talk about just sort of pure imaginaries first, and then that gets us into complex numbers, are a combination of real numbers, which we've been working with an imaginary part, and we'll go from there. Okay, so complex numbers. So where this all comes from is it possible to take the square root of a negative number? Well, let's see, like the square root of 4. This is a positive number, I know, but how would we take the square? What does the square root of 4 mean? What times itself is equal to 4? So 4 is 2 times 2. Oh, there it is. Positive 2 times positive 2. That is 4. So we could say the square root of 4 is just 2, right? So square root of 4 is 2. So it's the number that multiplies by itself. However, there's also, we could have taken negative 2 times negative 2, right? That also would give us positive 4. So we could also say that negative 2 is a square root. So oftentimes when we're taking a square root, we just say, okay, it's going to give us 2 answers. Typically, we focus on the positive answer. But, you know, square root of 4, because it's a positive number, would be, we just favor, oh, that's 2. It's not negative 2. It's going to be 2. However, if we're taking the square root of x, that's when we have to be careful, because x could be either 2 or negative 2. So that's where, when we go to solve something like this, we say that's going to be plus or minus, that x could be either one. It's x, but okay. So we can have, but notice it's the same number, right? They're either both positive or both negative. That's both the same number. What happens if one of them's positive and one of them's negative? Well then, yeah, that's going to give us negative 4. and they're not the same. So that's really, I mean, they're one's here and one's here. They're on the opposites, so they're not the same number. This is blowing the concept of a square root. So is there any way we could find a square root of -4? What's that? Okay, we have to make something up. We can't do it with real numbers because it just doesn't. There's no number that's both positive and negative at the same time. Well, maybe 0, but then that doesn't do much. So unless we invent something new, which someone decided, okay, let's just say, actually, all they had to invent was the square root of -1. They said, we don't know what it is, but we'll just say it's I. Why not? We'll make it up. And so I is a number. It's a, yeah, you say, well, no, it's a letter, but I is a number that if we square it, we're going to get -1. Okay, can't do that with real numbers, so it's a completely fabricated number. The cool part is in engineering and stuff, it actually it works. It gives us something in the physical world that works. Again, if you've got all our little electronics, these chips, what they've done is they pack so much onto the chips, they're actually using imaginary space when they put all the programming to get these chips down to the size that we can carry the computing power in our pocket of what used to fill a whole room with tubes and stuff, Actually, my dad was, he was an engineer, worked for Boeing, was on the Apollo project, it's in the man to the moon in the late 60s. He actually was an engineer he told me the 12th chamber engine in the Apollo rocket. So he's a rocket scientist. I'm not, but, and then he went over to computers. He worked for a trucking company. He was doing the computing part, and he told me when they first the computer filled the whole first floor of the building they were in. That was the size, and it didn't have the power that we have in these little phones now. And the reason is because on these little chips, they found a way to use imaginary numbers to get all this stuff down to such small size. So this made-up number is actually pretty important. But so we start using I. So something like square root of 4, we know that what we do is we break this down, and basically the square root of 4 times the square root of -1. So we're going to say square root of 4, we know what that is. That's 2. Square root of -1, that's I. So now we have a method to deal with square roots of negative numbers. That's all it is. It's all invented. Do we know if it would really work? Probably the person who didn't, but they said, well, it's a nice little tool. Let's just see. And then, again, applications for this were invented. And so we can do this. The part that gives us a negative square root, that would be an imaginary number. And then there might be a part of the answer that's also a real number, so that's the A part. And again, 2i as an imaginary number, we could think of it as 0 plus 2i. So there's always a real part. If it's not showing, if I just give you 2i, the real part is 0. Okay, we don't show it. But I could also list numbers like they've got down here, -1 plus 8i. So -1 is the real part, 8i is the imaginary part, and it came about because there was a square root of a negative number somewhere, right? So that's what a complex number is. Involves some kind of a square root of a negative number. It's completely imaginary. You can't graph it on your calculators. Again, but yet it is valuable for those who are going into electrical engineering, or when you're paring things down, you'll probably see these applications. And again, it's very technical, but it's there. So now that any questions on complex numbers? Does that make sense? Call it imaginary because it is imaginary. You just made up. We use the I and just say it, and that we do this in math. It is because I say it is. I made it up, or somebody made it up, and everyone else, okay, let's agree, and hey, wow, it's actually valuable. And that's the cool part about math. Some of it isn't. We always think math is sort of this 2 plus 2 is 4. It's, you can show it, you can do it. But there's all this parts of math that's so abstract and it's made up. But in the end, it ends up being actually useful. Okay, so here's two imaginary numbers. How do we go about adding them? First of all, if you have a TI-84, you could actually your calculator will be able to handle this. You could just enter it in. There is a little button for I believe it's under either the decimal or under the 0. I didn't bring mine with me, but there's actually a little I, a blue I, somewhere on the keyboard. So you hit second, and then you could put the I in there. So you could enter this into your TI-84 calculator. It will give you the answer, but what's it really doing? All it's doing here is we're combining like terms. So the like terms, the 3, the 6, and the 3 are like terms because those are the real parts. So we add the real parts together, and then we add the imaginary parts together. And just kind of keep the signs the same. So we just add everything together. 3 plus or 6 plus 3 is 9. And then the I parts, we treat that I as a sort of as a variable if we wanted to, but it's like terms. So -6 plus -5 is -11. And that's a -11i. So we would write that. We wouldn't put plus minus. We'd just put 9 minus 11i. Okay, so adding complex numbers, just add like terms. Add the real parts, add the imaginary parts, we're good to go. Subtracting. Pretty much the same thing, except you have to remember to do what with that negative sign? Perfect. Distribute it through. So the +4 becomes a -4, and the -3 becomes a +3. And then we're just looking at it. I got 2 plus, oh actually 2 minus 4, right? I'll make sure you get this. Maybe I should write it out. 2 minus 4. And then I'm going to have -2i plus 3i. -2i plus 3i. So 2 minus 4 gives us -2. -2 plus 3 gives us a +1i. So we just write that as that. So -2 plus I. Again, TI-84 calculator, you enter it in, use the I button. It will actually calculate this and give you the answer. What else can we do? We can also multiply. So if we're going to multiply two complex numbers, what do you think we're going to need to do here? We're going to get an I squared, and then we're going to have to remember, because I'd always forget that I squared becomes what? -1. So we're going to translate. But we use a FOIL, so we're going to do actually 4 multiplications here, right? We're going to take 6 times 2. Gives us 12. We're going to take 6 times -4i, -24i. Then we're going to take -5i times 2 is -10i. And then this is where we get the I squared. We take these last ones, -5i times -4i. We're going to get a +20i times I, which is I squared. We're not yet done, right? Because we've got some like terms in the middle, and we've got an I squared, which is something that actually becomes -1. It becomes a real number. And like Pinocchio wanted to be a real boy, right? But he kept lying. And so at least imaginary numbers don't have a nose, so they don't grow. Okay, so this becomes 12, -24, and -10. That gives us a -34. I, 20, I'll kind of do the step, times -1, because I squared is -1. And so that's going to give us a -20 here, and 12. So -20 and 12 is -8, right? And then -34i, that's still there. So that would be our final answer there. Okay, so a few in the homework they'll have a few of these, adding them, subtracting them, multiplying them. Again, if you've got the TI-84, if you enter this in just as it is with the I, it'll do it for you. It's kind of cool. Gives you your answer. Way to check, way to do it. But just know how it's just foiling it out, and it's converting that I squared to a -1. We okay so far? All right. Be honest with me if you're not. So now, what about division? Well, this is a part that in my other class we don't even get into this, but since you guys are engineers, we're going to get into it. So how do we deal with when we're dividing by something with imagine a complex number? Okay. What we're going to do is because it's not really in standard form, it's not imaginary number plus, it's not complex, it's not real number plus an imaginary, right? It's this fraction thing. So it's not in standard form. It's still perfectly fine number, but it's not in standard form. So what we do is we do something, we multiply by what we call the conjugate. And what's a conjugate? Well, the easiest way is just kind of show what it is. It's got the opposite sign in the middle. So what we're going to do is we're going to multiply by 1 minus I squared. But we can't, that actually will change it, won't it? We just multiply by something. But what if we multiply by 1? Does 1 ever change anything if you multiply? 50 million times 1 is still 50 million, right? So the thing is in math we found a unique way to multiply by 1. The same thing in the top as this in the bottom, and we'll get this is now multiplying by 1, so we're not really changing anything. We'll change how it looks, that's what the goal is, but watch what happens. So we'll do the top part first because we just done this, right? 8 times this we're going to distribute through, so we get 8 minus 8i in the top. So that's sort of the easy part. In the bottom, we're going to see why we use the conjugate, because what's going to happen is it's going to get rid of the imaginary part. And so we'll just have a real part. So we do FOIL again, because we've done this, multiplying these. So I have 1 times 1 is 1. So I did that part. And then I'm going to have 1 times negative I. So that's negative I. We get I times 1. So that's plus I. So see how the negative I and the plus I, they're going to cancel out. The i's are going to disappear. And then the last part, we get I times I. That's going to do that too soon. Positive times a negative is negative. We get negative I squared. Oh, we might have problems with this. Oh well. 8 minus 8i. These are going to cancel, right? Positive and a negative are 0. I squared is negative, so we get negative 1, which is a positive 1. Okay, we're going to be okay. 1 plus 1. I thought I was going to get 0, and I said, oh, this is a bad example. But 1 plus 1 is 2. And so this is still not quite in what we would call standard form. Remember, standard form is going to be a plus bi. So we divide both of these by 2. So we distribute the 2 with division. I'll write it as 8 over 2 minus 8i over 2. So we're going to get 4 minus 4i as our final answer. Okay, so division is a little bit more complicated but the first step is to it's not really to try to do the division, but to get rid of the denominator by multiplying by the conjugate. And we'll take a look at a little bit more complicated example, and we'll see how this one will work very similarly, but it's a little messier, right? Yes? Say that again? This one here? Yeah, so that I squared. So this is minus I squared, and the thing we always have to remember is I squared equals negative 1. That was the definition. Why is it? Because we said it was. It's so that's always the one that got me. It is because that's the definition of an imaginary number. And we're subtracting it, so we're subtracting a negative 1. It becomes a positive 1, and so we get 1 plus 1 is 2. Sorry, yeah. Good. Thanks for asking. Yeah. So if you see anything that you're not understanding, it's usually the simple stuff we don't understand, but then it's also that's going to block us because I don't see what he really did there, and it always sits with you, and you say it must probably some simple thing. But if you have a question, there's other people that are questioning the same. Okay. All right. So what's our conjugate going to be here?
5 minus 2.
Perfect. It's just going to be 5 minus 2i. So that's the first thing. If we do it in the bottom, we got to do it in the top because that means now we're only multiplying by 1. And we can see it's going to be a little bit more complicated than what we have, but we can do it, right? And again, if you got your TI-84 calculator, it's done. Actually, you just entered this in. You don't have to multiply by the conjugate. It will give it to you in the right form. Again, I always recommend doing that as a good form. You could do it on a test, but it's also good to know what's going on. Look, I think it's either the 0 or the period, and right above it, one of those, it'll have a little I. In fact, let me know. It's either the period or it's the decimal, I guess. Okay, was it the decimal or was it? Yeah, that period or the decimal. So right above that, you'll do second decimal, and that gives you your I. And your calculator handles these beautifully. Okay. So if you want to get through the homework fast and then come back later, that's fine too. Okay, so let's go ahead. I don't know, do the top or bottom first, but remember it's going to be foiling. So 3 times 5 is 15. 3 times negative 2i is negative 6i. And then we have 7i times 5 is going to be positive 35i. And then we get 7i times negative 2i is negative 14i squared. So notice the top was a little messier. The bottom, we end up with 5 times 5 is 25. You could skip this part if once you start to see it, but 5 times negative 2 is going to be negative 10i. And then 2i times 5 is positive 10i. So if you don't get these canceling out, you chose the wrong conjugate. You did something, but by choosing the conjugate, that's what we're making this happen. So that's the other part of math is, but then a lot of times we get surprised. Why did those cancel? Because this technique makes that happen. So when we choose the right things, things cancel and it all works out nicely. If it's not working out nicely, we got to go back and fix it. And then the last part, 2i times negative 2i, we get negative 4i squared. Now it doesn't just disappear, but the I will go away because we've got the definition I squared is negative 1. The middle pieces, negative 10 and positive 10 cancel out. This becomes negative 4 times negative 1. So that's positive 4. Oh, wait. Yeah, positive 4. Let me just go here. So we're going to get 25 plus 4 in the denominator, which is just the number 29. In the top, we'll have 15. Well, actually, let's do the same thing here. I squared is negative 1, so this becomes minus 14 times negative 1. That's going to be positive 14. Positive 14 and positive 15 is 29. Negative 6 and 35 is positive 29i. Wow, that's kind of cool. And so we've got 29 plus 29i over 29. We distribute that 29 by division, right? So we divide both the top. The 29, I guess I'll write it out. 29 divided by 29 plus 29i divided by 29. That's 1, that's 1, so we get 1 plus I. So this complicated thing actually is just 1 plus I. So we simplify down, and again, if we're doing some kind of research, maybe this is a lot easier to work with, 1 plus I, than instead of this complicated thing that might have come from some of our data or something. Okay, so we can simplify, but again, TI-84 calculators, we just plug this in as is, and it will come up with the right answer. Just be careful if you enter like 3 plus 7i and you just do a division sign, and then you do 5 plus 2i, what's going to happen? Order of operations, it's going to do that first, and then it's going to add, so it's not going to give you the right answer. So when you're using your calculator, make sure you either have it in a fraction mode, or you put some parentheses around the top and the bottom, so it does it in correct order of operations. Okay, so that's part of the thing, is make sure, just because it went in the calculator doesn't mean it's correct. If you know, as we said, I used to do computer programming, garbage in, garbage out. So if you don't tell your computer, your calculator will do exactly what you tell it to do, not what you want it to do. So make sure you're speaking its language, and it follows order of operations. So got to use the computer accent, not the human accent. So it'll all work. So far, so good? Yes. Yes. In fact, you're encouraged. I don't know how I wouldn't be able to pass the exam without a calculator. No. So here's the thing on, if you get, I guess I haven't seen the exam. Sometimes now, like in calculus, there's certain problems. When you get to calculus, I taught the 265. Some of them are multiple choice. So if you choose the right answer, you get the points whether you showed work or not. Showing work can sometimes help, because if you got a lot of correct work, then we can go back and we can give some partial credit. So it's always good to show your work. There are ones in the calculus that say show your work, because they want you to take they want to know that, and so those are graded as an essay and such. When I see the exams for this one, I'll let you know if they have those on here. If there is a question that says show your work, then yes, we're going to want to see it. So I got to be careful. But to me, if you can get to a correct answer, at least put that you're going to get that part right. And I won't call it docking points, but on those types, though, there's like there's so many points for the right answer. There's so many points for showing work. And as we get a little bit closer, when I see that, I'll let you know if it's needed or not. Okay. But definitely, at least focus on finding a technique, and using the graphing calculator is a great technique to get to an answer. Because if you can get to the right answer, we can talk about how to remanufacture the work if need be. So there's tricky ways around that. Okay. But especially engineers, what we want to do is we want to know a method, especially if it uses technology. How do I get to that correct answer? And that's what the engineering school wants you to be able to do. I had a math teacher who was a colleague of mine. He was an engineer first and became a math teacher second, and he always reminded us, as engineers, they don't want to see your handwork. They want to see that you ran it through a computer. So on the engineering side, your work might be beautiful, but they want to see the correct answer. Okay. Okay. Oh, now, okay. So this actually is going to bridge us over. We're going to use imaginary numbers, but it's also going to take us into the quadratic formula. So it kind of ties us into the next section. We go till 10:50. Yeah, we got plenty of time. So we're going to be good and strong through the quadratics, and then that still leaves that open time there. So what I want to talk about first is this technique. And again, I don't do this in my other class because we don't do the factoring and the stuff that we're going to be having you do in this STEM-based course. But we need something to complete the square. So what I want you to do is, I'm giving you a completed square, x plus 5 squared. That's what's called a square, right? If I square it out. What I want to do is I'm going to square it out, and this is going to help answer if I've got just sort of a part of a quadratic that isn't quite a complete square. How can I make it a complete square? Okay, so it's a little technique. Some of you maybe have used this and remember it. That's great, but I want to get there. So what I'm going to do is I'm going to FOIL this out, x plus 5. And I want to look at the relationship of what I end up with. So x times x is x squared. X plus 5 is 5x. There's another 5x. And then the last part here is 5 times 5 is 25. So when I see a square that's been multiplied out, the trinomial, there's a relationship here between this number, and this number. So when I go to factor a complete square, I want to factor it into x plus something, right? And if I had this, how do I know what I need? So here's the question that comes up, is we'll be given a question like x squared plus 10x, and we want to make that a complete squared. How do I know what to add to this to make it a complete square? I know I need 25 because I can see it here, but again, if I was just given this problem, if this is all I knew from this stuff, how could I figure out what I need to add? Would it be okay to say that I need to add half of this, right? 10 divided by 2 is 5. Okay, that's what it's going to be. I need to add half of it, so I need to take 10 and divide it by 2. And then I need to square that. 10 divided by 2 is 5. 5 squared is 25. That's how I get to that. So we're not going to have you take a bunch of squares and foil them out, but that's where this all comes from. What we're going to do is we're going to give you some non-completed squares, and we're going to have you complete them by adding it. And again, what we do, you do change it if you just add a number, but if you add that number and subtract that number, that's like adding 0. So that's the trick we're going to use. And we're going to do this a little bit, not a lot, but this gives us a complete square. And once we've completed the square, we then know it will factor into 10 divided by 2 is 5. It factors into this once we've completed a square. Okay, so that's the tool we're going to use. And then this is something new that I made up. I can't remember. So, okay, here's an example. I've got x squared plus b over ax. What do I need to add to this to complete it? I need to add half of this number, b over a divided by 2, and then what else do I need to? I need to square it, right? So that's the steps I'm going to go through. What we'll see is this is x squared plus b over ax. B over a divided by 2 ends up being b over 2a. And again, we're going to square this. And so this becomes x squared plus b over ax plus b squared over 4a squared. Okay. And so far you're looking, why were we doing this? It's because what we're going to do next. So it's sort of this partial step. And I'll be honest with you, I haven't done this. What we're going to do is we're going to derive the quadratic formula. When we're done with it, all you need to do is remember or memorize the quadratic formula. That's what we're going to use. But I want you to see the steps so that you can say that everything I've done to get to it is valid to do. You don't have to be able to do this on your own. If you want to and you have fun with it, more power to you. Go ahead and do it. But what we're going to do is we're going to start with just the general quadratic formula. We're going to complete the square. We're going to do a few steps, complete the square, and we're going to end up with the quadratic formula. And then we're going to use that quadratic formula to do some things. Okay, but so far is what I've done. Have you followed sort of along that I'm just taking an incomplete square, a quadratic, adding what I need to make it a complete square. So then at the very end of the day, I can say that this part will factor into x plus b over 2a squared. Okay, because I'm going to need that technique in my solving part. Okay, so I'm going to need to be able to do that, and you'll see me do that. And then I'm going to take a square root because I want to solve for x, and it'll all work. Okay, and again, remember, you don't have to be able to do this. I just want you to follow along so that you can see each step I did is mathematically appropriate. All you need to be able to do is use the final quadratic formula. And does anyone remember what that is? So we're going to come up and we're going to start with the quadratic equation. We're going to do this, but we're not going to test you on it or anything. So it's just you just kind of follow along. You don't have to necessarily take notes. So we're going to start with the standard as step one. Let's see what. Okay. Notice when we go to complete a square, we need to have a 1 in front of the x squared term. And it also helps if we just have the things with the x's instead of having the c here as well. So we'll do two things. We're going to divide everything by a first, right? Divide this whole side by a, and then we divide 0 by a, which is nice because 0 divided by a is still 0, right? So we get x squared plus b over ax. Remember, that's what we had on that other page. Go back, there it is. That's what we started with. And so we'll sort of take this result, but and then what we're going to do is we're going to subtract c over a, so it ends up on the other side. Is that okay? So I took that equation, divided everything by a, which is as long as I do the same thing to both sides, that's copacetic, right? It's okay. I haven't broken any rules. No mathematical police are coming in and arresting me or anything, so that's good. And then I just subtract c over a from both sides, and so we've got over there. So now I've got the sides with the x's. What I'm going to do is complete the square, which we've already done. So I'm going to take x squared plus b over ax, and I'm going to add, what did I end up adding? I'm going to add this, but I'm actually going to add it in its form like this, b squared over 4ac. So b squared over 4a squared. But my technique is to, again, I've got an equation. I can do anything I want as long as I do the same thing to both sides. So I'm going to add it over here as well. Is that good? And again, if you sort of get lost at any time, just holler out, and because I can explain it now, but if I have to go back 3 steps, it might not make as much sense. So all I'm doing is adding a number, and I can add anything. I could add 2 to both sides, but this is the one I want to add because this is going to complete the square for me. And again, remember, all this stuff that we're doing right now, it took really smart people about 300 years to figure this out. Back in Tartaglia, I think, or I might get the names. It was a Italian guy, hot-tempered Italian guy who came up with this method. And then somebody else stole it from him and said that he did it. But anyway, that's intrigue. So that's the history. This was a pretty big deal if you could come up with a general way to solve them. So remember this side. The reason we added this is this side will all now become the completed square of x squared. No, not x squared. Just becomes x plus b over 2a squared. And again, that's the thing, is how do we know? Well, because we made it into a perfect square, it's going to be whatever was in front of the x, half of what was in the front of the x. And if I square that, that's what it'll become. And again, you could square it out and you'll see you'll get what you want. What I want you to just see is that from what we did on the other page, this is appropriate. Okay, again, you don't have to memorize, you don't have to do this, but then on this side, to be able to add these together, what do we need? We need a common denominator, right? So I need to multiply. I just got a. I need 4a squared in the bottom, so I need to multiply both the bottom and the top by 4a. So then I'll have a common denominator, and I'll sort of switch the order. I'll put the b squared first, minus 4ac, right? And they've got a common denominator. I'll kind of go back here. Remember, this is what we're looking. So now we've got a b squared minus 4ac, so that's looking kind of good. We've only got 2a down here, but watch, that's going to take care of itself. So we've got x plus b over 2a squared equals b squared minus 4ac over 4a squared. And now we want to solve for x. So what do? Square root of both sides. And so a square root undoes a square. This is an inverse function sort of thing that we were just talking about last week. So we end up with just x plus b over 2a on this side. On the other side, well, the top numerator is just in a square root. But look at the bottom. What's the square root of 4ac? Or sorry, 4a squared, right? Square root of 4a squared. That's a square. That's 2a, right? 4 is square root of 4 is 2. Square root of a squared is a. There's our 2a. And now to solve for x, we just have one more step. Subtract b over 2a from both sides. So x equals, we'll put this first. And remember, when we take a square root, that's where we got the plus or minus. So since that part's still a square root, I'll put the plus or minus there. So that's what's going to happen. And so when we subtract this, we're going to get the minus b here. 2a and 2a, they've already got a common denominator. Plus or minus the square root of b squared minus 4ac over 2a. So you just saw 300 years of math history in about 5 minutes. Yes.
What do you call this formula?
We call this the quadratic formula. So, yeah. So we start off with the quadratic equation, ax squared. So this is a general one. We end up with what they call it, just the quadratic formula. And you'll see in the homework that they will say, use the quadratic formula to solve this. And so they'll give you a general quadratic, and all you have to do is you plug in the values for a, b, and c into this formula, and you get the solution. The solution, remember, it's all set up with the equation equal to 0. That means the y value is 0. Where is the y value on a graph equal to 0? The x-axis.
When you subtracted b squared and 4ac, like the denominator, weren't they supposed to like put together?
Here?
Yeah.
So 4a squared, since they have a common denominator, remember when you add two fractions with common denominators, you get that same. So it doesn't become, you don't add them together or subtract them. It's just 4a squared. So it's got the common denominator here, and then it's b squared minus 4ac. Does that help? Okay. Okay. So yeah, so there's a lot of things in here that, we got to. Fractions is usually the things most of us are kind of most rusty about. So we had to do that. Completing the square, we don't always do that, so that was sort of a technique. But I just want you to see that it's something that we can derive, and that's how we get there. What we're going to do now is we're going to use it. And this is so when you go through the homework, you're not have to go repeat these steps or anything. But I wanted you to at least see the techniques for getting through there. Because, again, especially as you go on into calculus, they're going to have you showing your work more and more. Okay, so use the quadratic formula to solve for x. So first thing we do is we identify what is a, what is b, and what is c. And to solve, we have to have that quadratic equation equal to 0. If it's not, we've got to do a little work so it's equal to 0. Okay, and so we take our quadratic formula. Oops, it's almost done. Where is my... Let's keep everything... This thing disappeared on me. Okay. This down. There we go. So we're going to say x equals minus b. B is positive 2. So we put that in there. Plus or minus 2 squared minus 4 times 3 times 5 divided by 2 times 3, which is a. So it's just take those numbers, plug them in. We'll do the math, and we're going to see, you might anticipate we're going to get, it looks like 2 to the 9th, that's 2 squared. Okay, we're going to get a negative inside of a square root, which is going to give us a complex number, right? So we've got negative 2 plus or minus square root, so we end up with, I'm just going to do some scratch work over here. 2 squared is 4. 4 times 3 times 5, 12 times 5, that's 60. Right? 4 minus 60, so we're going to have the square root of negative 56. And in the denominator, 2 times 3 is 6. I said 56, and why did I write 59? You see how I... for some reason, I want to keep right 56, right? The thing is a lot of times in homework, this is an answer. They may want you to write it as, it's actually 2 answers, right? Because we have a plus and a minus. The thing is can this square root of negative 56 be reduced? Well, in a sense, yes, it can be written as a square root of 56i, right? That negative square root becomes an I on the outside. But square root of 56, can that also be broken down a little bit more? Is there a perfect square inside of 56? 56 is 8 times 7, is that right? So the process we go through is, well, 56 is 8 times 7. 8 is 4 times 2, because I'm looking for a perfect square, so I'm looking for a number like 4, 9, anything that's a perfect square. So this is going to be the square root of 4. I'm going to take the extra 2 and times 17, or 7 gives us 14. Square root of 4 is 2. Square root of 14, and then I. So this negative square root of 56, that's going to become negative 2 plus or minus 2 square root of 14 I, all divided by 6. 6 has a 2 in it, right? So we can cancel, we can divide out a 2 from all of these numbers. 2 divided by 2 is 1, so I get a negative 1. This 2 divided by 2 is 1. I get square root of 14. And 6 divided by 2 is 3. And again, if you want to, if they ask for it in standard form, our final answer would be negative 1/3 plus square root of 14I and negative 1/3 minus square root of 14I. Okay, so very detailed. Again, notice we didn't have to derive the formula, but we have to remember that formula for use. Yes. Six. It would, well, square root of 36 is 6, so it would be just 6I. Yes, sir.
How come on your final answer the square root of 14I isn't also 1/3? Isn't it also being divided by
Thank
2?
you. Yeah, yeah. I made it up as I went. You're right. So yeah, we have to distribute. Thank you. Have to distribute that 3 to both of those terms. You can't just. I was already thinking of the next problem, and that's my problem. Is I move on too fast. Thank you. So yeah, that 3 has to distribute to both of them. There, I did break the rules. The police might have come in and arrested me for breaking the. Right, right. Sure. No, we still, that number we can still divide by 2. Yeah. Okay, so I've got one more and then we'll do this, and actually we went a little deeper into this. You'll probably, if you want to start on the quadratic part, you can, but you'll see that we're going to do a lot of these types of problems. So I think I'm going to, we'll finish this one up, and then on Thursday we'll do the quadratic formula and the other one. Okay, so what do we do here? This is not a quadratic yet, is it? Square both sides, and we're going to get a quadratic. So sometimes there's these methods for solving. It's not a quadratic yet, but the only way we can solve this is to square both sides, and then now we can see we're going to have an x squared. It's going to become quadratic. So if we square both sides, the square takes off the square root. Again, going back to the inverse functions, we get 6x minus 16 equals x squared. Remember, we need to use a quadratic formula. We need to get it equal to 0. So I like having the x squared positive if I can, so I'll subtract 6x and I'll add 16 to both sides. And that's going to give us 0 on this side, x squared minus 6x plus 16. 8 times 2. It actually might factor. No, it won't factor. So sometimes you can get by with factoring these, but because it's a plus 16 and minus 6, it won't factor. Okay, so we need to use the quadratic formula. We do that, and remember that is back here, minus b plus or minus b squared minus 4ac over 2a. It's kind of, I don't know if I told you guys, but I taught in Kazakhstan for a year. I was on sabbatical, and it was a talented and gifted school. So we had 8 students in our class, and we were team teaching. So I was teaching with either a Kazakh teacher or a Russian-speaking teacher. They spoke Kazakh or Russian, but they didn't speak English. I spoke English, but I didn't speak Russian or Kazakh. So if we wanted to talk to the teachers, we actually talked to the students, and they translated for us. Well, it's kind of cool. But what was amazing to me is in the Russian system, they teach them to do this stuff in their heads. And the student would bring up a problem. He says, I got the answer as this. And I said, how'd you get that formula? And they could plug it into the quadratic formula in their head and do it. Wow, that's amazing. I have problems when I do it on paper. So, but I thought it was kind of cool. So anyway, minus b. So this is a here. A is going to be 1. B is going to be negative 6. And C is going to be positive 16. So we'll see what we end up with. So we get minus b, which is minus negative 6, going to be positive, plus or minus square root negative 6 squared minus 4 times a is 1, times 16. So notice we're going to get a big negative there, all over 2 times a, which is 2 times 1. So we get a positive 6 plus or minus square root of 36. 4 times 16 is going to be 40, 60, 64? Okay, thank you. See, I can barely do the multiplication in my head, so let alone the whole equation. All over 2. And then 36 minus 64 is going to be a negative. Thank you. I was pausing for somebody to get it for me first. A negative 28. 6 plus or minus 2. And what we're going to see, so that's x equals 28 is 4 times 7. The 4 is a perfect square, so we can take that out. So I'm going to go over here. We get 6 plus or minus, I'll do this as 4 times 7 I all over 2. So that gives us 6 plus or minus 2 square root of 7 I over 2. And then distribute that, divide both of those terms in the top by 2. 6 divided by 2 is 3. 2 divided by 2 is 1. And so that would be our final answer. And again, sometimes in the homework they ask for you to do it as 2 separate answers. So it's 3 plus square root of 7i, 3 minus square root of 7i, and such. But notice sometimes we want to stop just at negative square root of 28, but we have to break those down a little bit more. Question? No, because this is going to be, this is the simplest form. If we graph this, we'll see it's a quadratic that doesn't cross the x-axis, so there is no real answer. There's only this complex answer. And so to get out a complex answer, that's really the only way is to use the quadratic formula. So these are, so we're going to do it on Thursday now, because I'm not going to try to do a half-hour lecture in 15 minutes or 10 minutes, 5 minutes. We will look at alternate ways because it does cross the x-axis, so there's factoring, there's other ways to solve it, but for these that I've presented, a quadratic formula is the only way. Questions? Okay, so don't feel overwhelmed about the I have to know how to get the quadratic formula. You don't. You just have to know how to use it, right? And don't even think about memorizing it. As you do these problems, you will come to remember it well enough. So I'll kind of do that. Excellent.